Okay, so I'll.
Thank you.
Okay, brilliant. Great. Well, thanks everyone for joining. Thanks everyone for joining. And I'm going to ask everyone to take their eyes off their Twitter accounts for the next 45 minutes. Carlos probably doesn't realize that by the time he's finished his seminar, Boris Johnson will probably have resigned, I think, is the hot money. So, yeah, don't keep watching the ticker going up. The number of government resignations have been. We're really pleased to have Carlos Cinelli with us. He is an assistant professor at Washington State University in Seattle, works in econometrics and has published interesting work in many areas, including negative controls and other causal inference methods, but has also ventured in into the Mendelian randomization field, and is going to talk about sensitivity analyses in Mendelian randomization. Thanks very much, Carlos.
Well, thank you. Thanks so much, George. So hi, everyone. Thank you for having me. It's a pleasure to be here. So like George said, I'm Carlos Cinelli from the Department of Statistics at the University of Washington. And I'm relatively new to Mendelian randomization, so I'm very excited to be talking to you. And then please feel free to interrupt me or correct anything, ask clarifying questions, and so on. So in this talk, the idea is to discuss how to assess the robustness of Mendelian randomization when we have residual biases such as residual population stratification, batch effects, and horizontal pleiotropy. And what is going to be different from the traditional tools that I think you have learned is that we are not going to assess the sensitivity or the robustness in that traditional sense of, for example, postulating a different mechanism for pleiotropy, such as the inside assumption. We're going to go over this in the end, and checking whether our conclusions still hold under this different assumption of how pleiotropy operates. What we're going to try to do is actually quantify how strong pleiotropy needs to be to change our conclusions or other biases too, not necessarily just pleiotropy, horizontal pleiotropy. And then we're going to try to convey that information in a way that hopefully makes sense for applied researchers to start thinking about, can I rule out this level of pleiotropy, or can I not rule out? Do I have enough knowledge to rule this out? So hopefully this is going to make sense as we progress. So this is joint work with Nathan, Brian, Shran, and Eliezer, and this paper has been recently published in Nature Communications. So please check it out, and I would love to hear what you think. So I want to start, as usual, I want to start with a brief introduction on Mendelian randomization. Now, since I know some of you are experts on MR, and many of you probably at least already have some familiarity with Mendelian randomization, I'm going to do something different. So we're not going to spend a whole lot of time just discussing the concept of what Mendelian randomization is. I'm just going to do a brief review and jump directly to the main threats of Mendelian randomization and to the sensitivity analysis part. Okay, so I think for this audience, this is probably appropriate. So most questions in the social and health sciences are questions of causal effect, such as, for instance, we want to know the effects of obesity on health and social outcomes. And here, with the caveat that we actually can't not measure obesity, we measure BMI, which has its own problems But for the whole talk, I'm going to ignore this measurement issue, okay, so, as most people do. And as we all know, randomized controlled trials are often infeasible or unethical in these settings. So for example, we cannot just simply randomize a bunch of people and do some intervention on them to reduce their obesity and another intervention on them. Well, and to increase their obesity to like more morbid levels, for example, and then follow them for several years. So this is not only technically infeasible for most of the time, because people are not going to comply, so you're going to have compliance issues. It's hard to think about what is the type of intervention that you would do that would actually be a surgical intervention that you actually just increase obesity and nothing else. But it's also unethical, right? So it would be very hard to come up with something that you can actually increase obesity to levels of that would put a lot of people's health in danger. So randomized controlled trials are often not a possibility for these types of studies. And so we're left with observational studies, but observational studies are likely to be biased because it's not like people choose to eat more or less at random. They self-select into eating more or into eating less. So you can have confounding, you can have selection biases, you can have all sorts of biases that mar observational studies that we are all familiar with. Oh, sorry. So that's where Mendelian randomization comes in. So the idea of Mendelian randomization is to exploit genetic variants, which I'm going to call here Z, as an instrumental variable to investigate the causal effect of an exposure trait D on an outcome trait Y. But the problem is that the validity of MR also depends on its own set of demanding assumptions. So mainly conditional on some observed covariates X. And we're going to discuss what this X is usually in traditional MR studies. We must have that the instrument Z must not itself be confounded with the outcome Y. And also that our instrument Z must affect the outcome Y only through its effect on the exposure D. So the first condition is the condition of ignorability of the instrument, if you're talking in econometrics terms, or unconfoundedness of the instrument. So the instrument cannot suffer from the same original sin that the exposure trait suffers, right? So otherwise, we're just back to a vanilla observational study. And the second condition is what people usually call the exclusion restriction, or in more genetics terms, it would be it would be the pleiotropy condition. We cannot have that our genetic instruments affects our outcome trait through other channels than the exposure trait itself. So these are the two main conditions in terms of identification of the causal effect. We also have a third condition, which is the relevance condition. So we must have that the genetic instrument does change the exposure trait. So we do have a connection from Z to D. This is mostly for statistical inference purposes. If this connection is not strong enough, we can have several problems. But we're going to focus in this talk. We're going to focus on these two conditions here, because the third condition, there are statistical methods that can use that can account for weak instruments. So this is the traditional DAG that you're going to see representing these assumptions. This is just one DAG, okay? There are many DAGs that can depict a valid instrumental variable. And so here we have our genetic instrument Z, our exposure trait D, our outcome trait Y, and here you have some X, which would be confounding. And in genetics, you could imagine this is, for example, a population structure, a population stratification. And we must account for this for Z to be a valid instrument. Now, the problem is that these conditions may be violated in several ways, such as population structure, batch effects, and horizontal pleiotropy. And to mitigate such concerns, researchers are usually advised to adjust for genomic principal components. So this would mitigate the problem of population structure or genomic batch indicators. This would hopefully mitigate some batch effects, although it could introduce a selection bias, which we're not going to go over here, but that's something that can happen as well. So it's a two-edged sword. And also, if you have some putative pleiotropic pathways, you should also see whether your estimates are robust to including or removing that variable, right? So let's see how a traditional MR study is going to be done in practice. So this is a real example. So previous studies used MR in the UK biobank data to assess the causal effect of BMI, body mass index. Here, our proxy for obesity on several social and health outcomes. So our exposure trait is BMI. And in particular, these studies found a statistically significant effect of BMI on diastolic blood pressure. So this is our outcome trait. I'm going to call here a DBP. And on Townsend Deprivation Index, which is a measure of socioeconomic status. And here I'm just going to call it deprivation. So in this example, our genetic instrument, Z, is a polygenic risk score. So this was derived from 97 SNPs or 97 genetic variants. People usually call this SNPs, found to be associated with a BMI in previous GWAS studies. So basically what you're going to do here is going to take this 97 SNPs, multiply by their betas found in the original GWAS study, and then you're going to create this score called the polygenic risk score, which can then use as a single instrumental variable. And to mitigate the concerns of these threats to MR that I was just mentioning, you're going to see, sorry, excuse me. You're going to see people adjusting for a set of covariates X, such as age, gender, genomic principal components, assessment center, batch indicators, as well as smoking and drinking status, right? So, for example, genomic principal components and assessment center and batch indicators would try to account for population structure and batch effects. And smoking and drinking status in this case are both putative pleiotropic pathways, especially for diastolic blood pressure. So in these original papers, these covariates were also adjusted for. Now, so these results, they rely on this strong assumption of zero residual population stratification, zero residual batch effects, and zero horizontal pleiotropy. And these are unlikely to hold, even adjusting for all these covariates X here. So why is that? So what are the main threats here to the validity of the study? So first, as we could have in the DAG on the left, we could still have uncontrolled population structure. So even though principal components are kind of magical, they seem to work very well for detecting certain types of latent confounding if you have certain structures. It could be the case that it does not account for all population structure. And if you have large genetic databases, that can be enough, even if the residual population bias is small, given enough sample size, that can still be enough to obtain false positive findings. So in this DAG on the left, adjusting for X is not sufficient for controlling our population structure. We also need to adjust for W. And in the DAG on the right, you have unblocked pleiotropic pathways, such as, for example, this other trait here called WHP. And adjusting for X is not sufficient to block such pathways. So here we would also need to adjust for W. And in general, of course, so these are just two illustrative DAGs. All these residual bias could be acting simultaneously. We're going to denote by W the set of all additional unmeasured variables that would be necessary for making Z a valid genetic instrument. So you could imagine W, for example, to represent the true population indicators, if you're talking about population structures, instead of the ones that are covered by principal components, or all necessary pleiotropic pathways that you would need to fully block horizontal pleiotropy, even accounting for, when you condition on a variable, you could be opening a colliding path, even accounting for this colliding paths too that you could open, and so on. So you would imagine this W is the necessary set for making Z a valid genetic instrument. And now our task is the following. So we're going to ask, how strong would these unmeasured variables W have to be such that if they were formally accounted for in the MR analysis, they would have changed the conclusions of the original MR study. So that's our goal. And to give a precise answer to this question, we need to understand again, go back again to what, how MR estimation works, so what MR is estimating. And we recall that the MR estimate is simply given by the ratio of two regression coefficients. Namely, we're going to have the ratio of the genetic association with the outcome divided by the genetic association with the exposure. So the numerator is, quote unquote, the effect of the genetic instrument on the outcome, and the denominator is the effect of genetic instrument on the exposure. Now, if we look at this association, we can see that it's easy to convince yourself that the MR estimate can only be 0 if and only if the numerator is 0. So you're only going to find a positive or a non-zero, sorry, not a positive or negative or non-zero MR estimate if you find that the genetic instrument is associated with the outcome. And the other thing that you can see here is in this ratio is that if you can make this denominator arbitrarily close to 0, either from the left or from the right, you could blow up the MR estimate. So the MR estimate can be made arbitrarily large if the denominator can be arbitrarily close to 0. And these two conclusions, so this holds for the point estimate, but the same reasoning actually holds also for statistical significance in the Anderson-Rubin or the Fiala approach. So you can only reject the null hypothesis of 0 effect if you can reject the null hypothesis of 0 genetic association with the outcome, and you're going to get unbounded confidence intervals only if you cannot reject that denominator or the genetic association with the exposure is 0. So basically, the sensitivity of the MR estimate boils down to the sensitivity of these two genetic associations, which are two regression coefficients. And why is that useful? Because since we reduce the problem of the sensitivity of Mendelian randomization to the problem of sensitivity analysis of the genetic associations, which are two OLS or regression coefficients, we can now leverage recent developments of sensitivity analysis for OLS to Mendelian randomization. In particular, we can leverage the sensitivity analysis tools of this paper published in 2020 on GRSSB for this task. And here in the presentation, I'm going to focus on using these tools to assess the sensitivity of the null hypothesis of 0 causal effect. And when we are interested in the hypothesis of 0 effect, just like I showed you before, the sensitivity of the genetic association with the outcome is exactly the sensitivity of the MR causal effect. We could also focus on other null hypotheses, but I'm going to mostly focus on the 0 null for our presentation. So now, how can we do this? Okay, so just to recap, we saw that the MR estimate is the ratio of these two genetic associations. This is 0 if and only if, so this is 0 if and only if this is also 0. So we're going to focus on assessing the sensitivity of the genetic association with the outcome, because this is the same as assessing the null hypothesis of 0 effect of the MR estimate. And how can we do that? So this is the only method I'm going to show. It's really simple. It's algebra of ordinary least squares. So the first thing we're going to do is we're going to take, we're going to parameterize the bias of our genetic association as a function of the partial square of these omitted variables. Okay, so this is the formula you would get. So this is actually an exact finite sample formula. It also holds for the population. And so this is how much your, so this is the genetic association you see, adjusting for X only. This is the genetic association you wish you had estimated, adjusting for both X and W. So Z is the instrument, Y is the outcome, outcome trait, X is the observed covariates. And we can recover what we wanted from what we have by simply positing the hypothetical strength of how much variation, how much residual variation these omitted variables explain of the genetic instrument and of the outcome trait. And we can also adjust how our standard errors would change. And with these formulas, we can compute for any postulated hypothetical strength of the omitted variables, how much our statistical tests would have changed, or how much our confidence intervals would have changed, and so on. We're going to see in practice how this works. Okay, but this is, so this first formula is saying, you give me the postulated strength of the omitted variables, and I'm going to tell you how your, for example, t-test would change, or your statistical significance would change. But we can also ask the inverse question, which is, give me what is the threshold that would invalidate my statistical inference. So what is the value that I need to believe? What is the minimum value of the strength of confounding that would break my statistical inference? So I need to believe that confounding is weaker than that. Otherwise, I cannot rule out problematic confounding or pleiotropy to invalidate my claims. And then we can compute that. So we're going to see that to make the genetic association equals to 0, we're going to conclude that how much the omitted variables explain of the genetic instrument needs to be at least greater than how much variation the genetic instrument explains of the trait itself. If the omitted variables cannot explain, if it's implausible that the omitted variables explain as much variation of the genetic instrument as the genetic instrument explains of the trait, then it's logically impossible for these omitted variables to explain away your effect. And we can also compute, so here we are not imposing any constraints on how much variation the latent variables explain of the trait. We can also account for both at the same time. So what is the minimal threshold, both on how much variation the latent variables explain of the instrument and how much variation they explain of the trait. This leads to the robustness value. And I'm going to explain in practice what it means. It's easier than explaining here. But the bottom line here is that this robustness value, which is going to be a threshold on both sensitive parameters at the same time, characterizing the minimal strength of these omitted variables, is a function simply of the F statistic of the genetic association of the instrument with the trait. And if you don't remember what the F statistic is also just a function of the partial square. It's just R squared divided by 1 minus R squared. So this is also very easy to compute. And you can compute just from summary statistics. You don't need the full data to compute these quantities. All right, so we have here, I give you a postulated strength of confounding. I can tell you how my inference changes. I can also tell you the inverse question: what is the minimal strength of confounding or pleiotropy that would break down inferences? And now there's a third tool that we're going to need, which is bounding the strength of the omitted variables relative to the strength of observed covariates. So this can be helpful to calibrate judgments about what is a plausible amount of strength of the omitted variables. And what we're going to do here is we're going to ask the researcher to say, you have some observed covariate xj, and how much stronger do you think this omitted variable w is relative to xj? And you're going to say, well, it's probably once, twice, or 3 times as strong, but it cannot be 4 times or 10 times as stronger than this observed covariate. If the researcher is able to make this type of claim, then this leads to bounds on the worst possible strength that these omitted variables could have. And then we could bound the size of the bias if W were as strong as, or multiple times as strong as, this specific observed covariate xj. So let's see this in practice, if that sounds a little bit abstract, but I think it's good to see the formulas just to see They are not complicated. This is just the algebra of ordinary least squares. So let's go back to our running example. So we were asking, so we saw that traditional MR using polygenic risk score found a statistical significant association of, or a statistical significant quote-unquote causal effect of BMI, both on diastolic blood pressure and deprivation. So how robust, now we're going to ask ourselves, how robust are these effects that we found to possible residual biases? It could be residual population stratification, residual batch effects, or residual pleiotropy. So here is our proposal for a minimal sensitivity reporting for MR. So we're going to start with the usual traditional MR results. So here we have the risk difference, for example, a 95% confidence intervals, and the p-value associated with these findings. So now what I'm asking you is to compute two extra quantities, and they are very simple quantities. The first one is the partial square, and the second one is the robustness value. So these are the two quantities that I discussed before. And these two quantities already are going to tell us a lot about the sensitivity of these MR estimates. So let's start with the partial square of the genetic association with the outcome. Now, this quantity, most MR researchers may already be familiar with because they are already advised to report the partial square of the genetic association of the polygenic risk score with the exposure trait. And the reason they do that is to assess the problem of weak instruments. So now what we are saying is that, well, you should also report the same partial square, but for the outcome trait, not just the exposure trait. And the reason is, not only this will give you a good idea of how much your genetic instrument explains of these traits itself, but this is also a measure of sensitivity to extreme confounding or extreme residual bias. And in what sense? So this partial square, so starting with the diastolic blood pressure, this partial square of 0.35%, 0.035% is telling us that in an extreme scenario, even if the omitted variables explained all remaining variation of diastolic blood pressure, they would need to explain at least 0.035% of the residual variation of the genetic instrument in order to fully eliminate the MR estimate. Or if you think about it in the other way, the genetic instrument will need to explain 0.035% of a certain trait, if you're talking about pleiotropic pathway, for this pleiotropic pathway fully explain away the association you see with diastolic blood pressure, even if this other trait explains 100% of the residual variation of diastolic blood pressure. So this is giving us what is the bare minimum strength that these omitted variables need to have to logically account for the association we see. And you can see that this number reduces to 0.002% for the case of deprivation. So a much weaker omitted variable is needed to explain away the observed association in deprivation. But this may be a true extreme scenario because we are not constraining how much the latent variables explain of diastolic blood pressure or how much they explain of deprivation. They could fully explain these traits. They could have a perfect deterministic relationship. It may not be plausible. So this leads to the robustness value. So the idea of the robustness value here is to account for both sensitivity parameters at the same time. So for example, the robustness values of 1.47% for diastolic blood pressure is telling us that if the genetic instrument explained 1.47% of, say, a pleiotropic trait, this trait will need to explain also at least 1.47% of the variation of diastolic blood pressure to make the MR effect estimate statistically significant at the 5% significance level here. So this alpha 0.05 is the significance level that you can choose. And note that for deprivation, again, the robustness value reduces to 0.08%. So these metrics are quantifying how strong these residual biases need to be in order to change the original conclusions of our analysis So this is analogous to if you study in epidemiology the corner field conditions to explain a risk ratio. So this is analogous to the corner field conditions, but you're explaining here a partial regression coefficient. In our case, to explain the minimal strength to explain not only the partial regression coefficient, but also the IV estimate, which is the ratio of two partial regression coefficients. But now it comes the hard part of sensitivity analysis, the plausibility judgment. So we're telling the researcher you would need a latent variable that explains, well, you need some latent variable that the polygenic risk scores explain 1.47% of this pleiotropic pathway. And then this trait would also need to explain 1.47% of diastolic blood pressure, and this would be problematic for you. Or if both of these values are below it, then this is safe. It means that it cannot explain away. But now the hard part is this a lot or is this too little? Is 1.47% or 0.08% something that I should worry about or should not? So this is the harder part of sensitivity analysis. And in many fields, people don't have a good idea of absolute judgments of what is a plausible strength or not. But you can correct me if I'm wrong, but I have been, when talking to people that work with genetics, it turns out that sometimes people do have a good idea of how heritable a trait is. So for example, you can imagine complex traits. It's hard to imagine a polygenic risk score explaining 10% of the variation of a complex trait and things like that. So sometimes you may have a good idea of this number, depending on context, is larger or not. But sometimes you may not, but you may have some idea of relative importance, or make judgments of how strong these variables could be relative to some observed covariates. So to aid experts in these judgments, we're not saying that this is something that is going to be the truth. It's just another tool to help you make sense of these numbers, because this is what you need to believe, right? In order to sustain your claim. We can bound the strength of the unobserved variables with the same strength or multiple of the strength of a group of covariates, such as observed principal components, observed batch effects, and observed putative pleiotropic pathways, such as alcohol and smoking. And then this can give you an idea whether the latent variables would need to be much stronger than the observed biases. So let's start, for example, with diastolic blood pressure. So you can see here that so in this column here, we have bounds on the strength of omitted variables W. If it were as strong as principal components, batch effects, or alcohol and smoking. And this is how much residual variation this W could explain of the polygenic risk score of the genetic instrument. And this is how much variation it could explain of the trait, the diastolic blood pressure. Now, if you look at these bounds, this is how the bound on the strength of confounding as strong as these variables. You can see that they are all below 1.47%. So this means that if confounding is as strong as observed bias, or if pleiotropy is as strong as observed pleiotropy, they cannot fully account, they cannot logically account for all the observed association we see between the genetic instrument and diastolic blood pressure. Okay. Now, so that's what I just said. So the effect of BMI on diastolic blood pressure is robust to biases as strong as observed principal components, batch effects, and alcohol and smoking. But now, if we change for the effect of deprivation, we see the opposite. So all the bounds are above the RV of 0.08%. So that means that the effect of BMI on deprivation is fragile to biases as strong as observed biases. So if you're not confident enough to say, maybe there is, it's impossible to have a pleiotropic pathway out there that I did not measure that would have the same strength or stronger strength than alcohol and smoking, then if you cannot make this claim, then it's easy to imagine confounders. We can show that it's possible to find confounders that would completely kill or even reverse the sign of the effect of diastolic of BMI on deprivation. So these tools are, so this is the minimal sensitivity reporting that we are proposing. And you can see that with this robustness statistics telling you what is the threshold, the minimal threshold for you to believe that you need to have about the confounding for you to sustain your claims. And this, at least these guidelines of relative importance of these unobserved variables relative to observed variables can already give you some sense of the strength of the results. Even if you don't have fully confidence yet on the results, at least now you know what you need to believe in a certain way, both in absolute terms and in relative terms, in order to sustain the claim. But we can also use some visual tools to explore these results further. So this is a sensitivity contour plot of the t-statistics for testing the null hypothesis of zero effect or zero causal effect for BMI on diastolic blood pressure. So in the x-axis, we have how much residual variation these unobserved variables explain of the polygenic risk score, or if you think about it, how much the polygenic risk score explains of a pleiotropic trait, for example. In the y-axis, we have how much, how strongly these omitted variables are associated with the outcome trait, in this case, diastolic blood pressure. So again, these two axes are measured in terms of partial square, indicating the percentage of unexplained variance, both in the genetic instrument and the outcome trait that these unmeasured variables explain. Now, the contour lines, they show us what would be the adjusted t-value we would have obtained had we adjusted for an omitted variable W with such a strength. So starting with the bottom left here, we have the original t-value for testing the null hypothesis of zero causal effect of BMI on diastolic blood pressure. And this is 9.7, so it's a statistically significant result, right? But this is assuming zero residual bias. So this is a traditional MR result. And as we move along the diagonal, we're hypothesizing omitted variables with increasing strength. So it's going to reduce the significance of our finding to eventually making it cross a critical contour line. And in this case, the critical contour is 1.96, which is the usual 5% significance level threshold. And these red diamonds here indicate the maximum strength that unobserved variables would have if they were 14 times as strong as the first 20 principal components, 7 times as strong as alcohol and smoking, 6 times as strong as observed batch effect and as assessment center indicators, and 1 times as strong as all these observed variables together. So here we're combining the explanatory power of principal components, alcohol, smoking, and batch and assessment center. And you can see that in this case, residual biases with such strengths would still not be strong enough to overturn the results of for diastolic blood pressure. And we can do the same plot for deprivation. And I'm not going to go over the plot again because it's literally the same thing. So the reading of the plot is the same. But in contrast with the previous result, we see now that the association or the causal effect of BMI on deprivation is much weaker and is susceptible to residual biases a fraction as strong as observed biases. All right. So these are the main tools that we're offering for people to help making sense of the robustness of their MR estimates or the sensitivity of their MR estimates. So these tools are not dispositive. They're helping you to leverage knowledge or to make sense of what you need to believe to sustain a certain claim. And now I just want to explain this in the context of other robustness tests we have in the literature and how these tools can help supplement this test. So we're not asking to replace this, other robustness tests you have for MR. This is something that is going to help you in the context of all these analysis that you can do to make sense of your results. So the prevailing proposals for sensitivity analysis for Mendelian randomization have focused on replacing the traditional IV assumptions of zero pleiotropy with alternative assumptions about how pleiotropy operates. So for example, we have the inside assumption, so is instrument strength independent of direct effects. For example, in MR-Egger, that's the main assumption you're going to make for using MR-Egger. You have other assumptions such as zero mode of pleiotropy and many others. So these are very useful tests because they are asking, if I make some slightly different assumption on how pleiotropy operates, will that change my result a lot? And you can do these robustness checks to assess whether your MR estimate is sensitive to these assumptions of how pleiotropy works, and certain assumptions are more defensible than others, right? But although an improvement over the very strong IV assumptions, this is not a magic bullet, because if you still have, for example, some residual population stratification or some residual batch effects, or even certain forms of pleiotropy, these approaches may still lead to highly statistically significant false findings in large genetic databases. So even if the inside assumption is violated just a little bit, this can be enough to, if you have 500,000 people, just like in the UK Biobank, this can be enough to make to lead to statistically significant false findings. So let's just see this in a simulation study. So this is the DAG illustrating our simulation setup. This is a traditional simulation that many papers have done before. So just following the literature here too. So here we have G is our genetic instrument. The genetic instruments are independent of each other. So that's why we don't show them all here. The genetic instruments affect our exposure trait, affect some observed covert X, which is a pleiotropic pathway here, and also affects some unobserved covert W that we do not measure. And you can see the way that we set up our simulation study here. So we're going to have 90 genetic variants, similar to our BMI example. The genetic effects are going to be drawn from a uniform 0.01 and 0.05. And we're going to pick small numbers also for these effects. And here for the simulation, we're going to pick similar effects for X and W. So if you know that, you could exploit that for sensitivity analysis, like we saw in our example. And notice that the way we're simulating here pleiotropy, both the inside assumption and the zero modal pleiotropy assumption are going to be slightly violated, okay? So the bias is almost zero. For example, the modal bias is almost zero, but it's not exactly zero. And also the inside assumption is violated because the effects are going to be correlated here. But to put these values in context, for if you simulate just a sample size of 10,000, 30,000 individuals, this level of pleiotropy will barely affect type 1 error for MR-Egger, for example. But if we consider larger sample sizes, this will lead to statistically significant findings, even if the zero effect. So let's just see here the results of the simulation. So first, let's start with a true null causal effect. So here, rejecting the null is a false positive. And we find high false positive rates across all methods. So that's not surprising. That should be the case because the signal is there. It's just the signal is not causal. And how can sensitivity analysis help here? So that's what I want to show. How it could complement these robustness checks, because notice what would happen here. So here you would run your traditional MR analysis, for example, using IVW or using the polygenic risk score as an instrument. Then you would run MR-Presso, MR-Egger, MR-Genius, MR-MBE, MR-Mix. So these are all different types of MR analysis. And they would all reject the null hypothesis, for example, and you just say, oh, my analysis is robust. But they are all rejecting the null hypothesis because we have a non-zero residual bias here. So all of them will lead to the same rejection. So sensitivity analysis can help here in the following sense. So first, if you do that relative comparison, what is the strength of the omitted variable relative to the strength of the observed variable that would nullify my conclusions, the sensitivity analysis in most of the time, or 95% of the time, would give you a number less than 1, warning the researcher that if there were some unobserved variable W as strong as this observed covariate X, this would be sufficient to nullify the study. Okay, so that's how the sensitivity analysis could help, saying, look, if you have something as strong as your observed covariate X, this is enough to kill your estimate. And also the robustness value would all be below 95% of the time would be below 0.6%. And this ought to tell you that if you have an omitted variable that explains 0.6% both of genetic instrument and of the outcome trait, this would be sufficient to overturn your conclusions. So now let's see the results for the true positive causal effect. So here, now rejecting the null hypothesis is good because there is a true causal effect, and we want to find this true causal effect. So all methods get it right because they were already rejecting when the true null was 0. Of course, it's going to still reject when the true causal effect is greater than 0. So the challenge here is not on rejecting the null hypothesis, but convincing the community that you reject it because there is a true cause effect and not because there are residual biases. So that's how sensitivity analysis could still help in this case, for example. So here you would see, for example, that 95% of the time you would get that your estimate would be robust to omitted variables as strong as the observed covariates. So if you had the knowledge to say, well, I think it's unlikely that omitted variables are as strong as the observed covariates X, then you would say, well, we would need to take something stronger than my observed covariate X, so maybe this is implausible, right? So that's how it could help you make an argument for the robustness of the claim. And the same thing for the robustness value. So here, all the robustness values will be above 2%. So if a critic wants to argue against your finding, they will need to come up with something. So for example, pleiotropic pathway, such that the genetic instrument would need to explain 2.5%, for example, of this pleiotropic pathway. And recall that the genetic instrument is usually made to predict the exposure trait and not this other pathway, which may, so it can be implausible that it explains 2.5% of the variation of this other trait, which is not the exposure trait, because that's not how the polygenic risk score was constructed. And also that this trait also explains 2.5% of the outcome trait to fully eliminate the findings. So the idea here again would be to combine all this evidence and help you make sense of the results. So you would have the traditional MR plus all the robustness tests against different types of pleiotropy, and plus the sensitivity analysis quantifying how strong these omitted variables need to be to overturn your results. And here, so this is just another simulation. It's almost the same thing. So I'm not gonna go over a lot. So basically what we're doing here, instead of varying the strength of the of the pleiotropy for all instruments, of all genetic instruments, we are just varying the number of valid variants. So from 20 until 90. So if you have 90 valid variants, it means that all analysis should give the correct answer. So here you have rejection rates close to 5%. Except MR Genius. This is a little unfair for MR Genius because I didn't discuss the identification assumption here, but you need a heteroscedastic instrument. In this setup, it's not heteroscedastic. Yeah, anyhow, so we don't need to go here, but the conclusions are basically the same. So the sensitivity analysis could help you by showing that you would correctly show you that weak confounding would be sufficient to kill away, to explain away your estimate in this scenario as well. So let me sum up so we have some time for questions. I think I'm already over time a little bit. So most Mendelian randomization studies will be imperfect in some way or another, such as having residual population stratification, residual batch effects, or horizontal pleiotropy.
But the bottom line here is that the MR study does not have to be perfect in order to be informative. So what matters is not whether certain assumptions hold exactly, but the extent to which certain conclusions are robust to plausible violation of such assumptions, right? If we want to be, if you want to have exact, perfect results, we're not gonna never do any study, right? So so we need to acknowledge that there are going to be imperfections and try to assess how sensitive our conclusions are to these imperfections. But the good news here is that assessing the sensitivity of an MR estimate is as easy as assessing the sensitivity of a regression estimate. So in particular for the zero null hypothesis, as I showed here, the sensitivity of MR reduces to the sensitivity of the genetic association with the outcome. And we can leverage all the sensitivity analysis tools that I showed you to assess the sensitivity of MR. And we have these two simple sensitivity statistics, the partial square and the robustness value, that can be used to easily communicate the minimum strength of residual biases that are needed to invalidate the results of an MR study. And whenever researchers are able to argue that they have credibly accounted for most of the population structure, such as with genomic principal components, or have measured non-important pleiotropic pathways, these variables can be leveraged to at least give you some idea of the plausible bounds on the strength of residual biases, and give us some idea of what would be the worst possible inferences due to these residual biases as strong as observed biases. So that's it. Thank you. So the paper is this one: robust Mendelian randomization in the presence of residual population stratification, batch effects, and horizontal pleiotropy. It's already online, published. It's open source, and you also have this related literature here and some recent extensions that we can discuss later if you guys want. And that's it. And sorry for running over time.
No, that's great. Thanks very much. If people have questions, if they're online, if you can put them in the Q&A, or if you can ask to be unmuted, you can ask them. Is anyone, any live human have any questions? So I'll ask one: is have you applied this to situations where we know that the MR answer must be wrong? So those sorts of situations are where you have a negative control which is impossible to be caused by your exposure. So for example, you use instruments for lifetime smoking, and then you look at outcomes at age 7, and you know, as people have done, and you know that it's not possible that no one smokes at age 7, so you know that's impossible. So you could then actually look at look at your sensitivity analyses and see what you can actually see, even when you know something cannot be true. Have you?
No, I didn't test to a clear-cut case like this. I tested for the controversial case of the good fat, bad fat. But the problem with so we did this because a reviewer asked, and the results actually made sense as well. But the problem with that is that, so here we have some limitation that we're addressing, is that we need the outcome to be continuous. We're not doing this with logistic regression, but now we have some tools or some extensions that allows us to do with the logistic regression. So when we did that in that case, we were using linear regression, and then there was this limitation. But that's very interesting. I think I definitely want to test that with these known cases. So maybe I'm going to follow up with you to know what are these clear-cut cases that we know it's impossible. And I can see two things that we can do here. So one is to see if the sensitivity analysis results make sense. But the other thing that could be useful is to use those negative controls to quantify the strength of residual biases, because we know whatever association we are seeing there is because of of bias, right? Because
Yeah.
if we know it's impossible to have the causal effect, then it's all due to something else.
Yeah.
So this could be used this could be useful to calibrate maybe for certain class of traits what the plausible strength of biases could be.
Yeah.
I don't know if it makes sense. We need to think about it, but it could be useful for that as well, actually, not just for testing the sensitivity itself, but for having an idea of the magnitude of how much variation
Yeah.
whatever biases would be working there. And I need to think what type of bias actually would be the main threat for this case. But
right.
to calibrate the strength, the plausible strength of these biases.
Yeah. So
does that make sense?
There's a second question from Steve Burgess. And Steve asks, how does this approach differ to e-values?
So the logic of the approach is the same in the sense of we are trying to quantify. So for example, the robustness value and the partial square. Oh, sorry, I didn't want to go over. I wanted to go back. So for example, the robustness value is similar to the e-value in that sense that it's trying to compute the minimal strength of both sensitivity parameters such that it nullifies some association. The difference is that the e-value is for risk ratios, and this is for partial regression coefficients, right? So basically that's the difference. So here we are asking, so the sensitive parameters are going to be different. So here the sensitive parameters are in terms of variance explained. So how much genetic variation, for example, the polygenic risk score could explain of the pleiotropic trait. Whereas in the e-value, you would be measuring this in terms of risk ratio. So what is the max of the risk ratio? They would change for a certain trait and so on. So the difference would be it's a different parameter and different formulas and different everything for that sense. The logic of the meaning of trying to find the threshold where the inference changes is the same. The partial square is a little different because here we're not putting any constraints on one of the associations, right? So this is the bare minimum strength that the genetic instrument must have with the latent variable only. Yeah, so the difference is mainly this, and then I guess you would need to think about what is more useful in your settings in terms of, can I think of the strength of confounding in terms of variation explained, genetic variation explained, for example, or heritability, which is a partial square measure, or things like that? Or do I want to think in terms of risk ratios? Is my outcome binary and other things like that? Does that make sense?
Yeah, thanks for that. And we've got another question from Wes Spiller. It says, great talk. Do your simulations include an interaction between Z and another covariate, presumably W? Curious if this motivates the inclusion of estimates using MR Genius, which would rely on this for sufficient statistical power.
Yeah, so that's a great question. So the MR Genius showed up here because a reviewer asked. And then the original simulation study, as you can see, does not have interactions, and it doesn't have heteroskedasticity. So it's unfair actually to MR Genius because basically the statistical power is 0 here, and the original MR Genius, now they have a correction that allows for weak instruments, but the original MR Genius is going to be it's going to have a weak instrument problem. And that's why you get this highly, this 100% false positive rates. But in the appendix, we do vary the strength of heteroskedasticity with the latent variable to see how sensitive the MR Genius would be. So yeah, so the inclusion here was mainly due to the publication process. But this is a little unfair for MR Genius in this setup here, this simulation study.
That's great. Thanks very much. So I apologize for saying you were from Washington State when you've got University of Washington behind, right, literally behind your head, and then I said you were from Washington State University. So
No, that's fine.
you're from University of Washington. That was really really great talk, and I'll email about the negative control idea. So so I think there's no more.
Yeah, I think this idea, it would be great actually.
Yeah.
To explore that. And
Oh.
one thing that was limiting us is that here we're focusing on continuous outcomes. But now we have some tools that allows us to do for binary outcomes as well. So,
Okay. Which, yeah, that would be some good examples.
Yeah,
Definitely some good examples there. So so thanks very much indeed for, especially for getting up so early to give us a seminar, and yeah, it's really interesting, and as I say, I'll email about the Fox to follow up. Brilliant.
well, thank you, George, thank you everyone.